Looking at homework number 12. So I'm on page 17. I'm on page 17. I think in here before we left yesterday, we talked about number 12. Yes? Did you draw it? I drew it. Did you draw it? Okay. What else do we say about number 12? Do what? BD bisects. What does that mean? Splits it in half. What does that mean? What does it do to this angle? What is that angle ABD and DBC? They're equal. You have values for both of them. You have expressions for both of them. What do you do with those expressions? Add them together. Is that what we did yesterday? Okay. It bisects it. It means angle ABD and DBC are related how? So what should you do with them? Set them equal to each other. Whoa!
What is that?
It means you have x squared. What's ABD? Tell me what ABD is.
X squared plus x plus 12.
Okay. And what is DBC?
Oh.
X squared plus 3x plus 4. You put an equal sign in between them and you solve for x. It's a lot easier than you think. Okay? I need to know that you can algebra. I mean, subtract x squared from both sides. Then it's gone. There's no more quadratic. Okay? Then you have x plus 12 equals 3x plus 4. And pretty sure you can solve that. I'm turning the page. Oh, maybe not everybody knows. Maybe not everybody knows. Number 14. It tells you something. You see the parentheses number underneath number 14. You see that? Do you know what it means? It's a lesson it goes back to. So turn back to lesson 2. Look at the properties. There were only 3 properties. We wrote them down. Go into that. What property justifies this? And that's all you have to say. Just tell me the property. Very good. So we're going to go back and look at it. We're on page 7. Page 7, properties. Go back and look at them. What about number 16? Oh, number 16. Let's draw it. So if you talked to me yesterday and I did not draw it, that's a bad thing. It's never good when you take things without drawing them. Number 16 is a good one. What did you draw for number 16? A number line. Are you going to put every number on this number line? What number should you put? Where do you begin? Where do you end? Okay? And if we wanted to know the midpoint, because it's asking for the midpoint, right? Okay, what does midpoint mean? The middle. So I think I gave an example from here to my house is 7 miles. What's the midpoint? 3.5. Okay? What do we have to find? What do we have to know to find the midpoint? The distance from here to my house, right? Now the difference is I started at 0 to 7, and the midpoint is 3.5, right? We didn't start at 0. Okay, so maybe we can go back and find what's the distance. How do you find the distance on a number line? Mm-hmm. And you get what? Do what? I like this, but there's one thing that's not quite right. What is she forgetting in her formula? All right, let's turn back. I think I'm on page 8 now. Yep, page 8. We can look at postulate 1, that second piece of postulate 1, or the distance. If you're reading that.
Absolute value.
The distance between 2 points is the absolute value of the difference of their coordinates. Okay, so we know distance can't be negative. Let's go ahead and be sure we put those absolute value signs there. So what is the distance from negative 142 to 53? 195 units. Are we done? Is that what they asked for? No. So what does the midpoint mean? You have to have half. You have to have a middle, right? So do we all logically see the middle has to be somewhere in between here? Okay? So when we divide 195 by 2, what do you get? 97.5. Is that our midpoint? Why? Because 97.5 is way over here. Okay? So does the midpoint have to be in there? Has to be between there. So what else about a midpoint do you know? Other than it cuts it in half. It cuts it into 2 congruent pieces. So do we know that this distance has to be 97.5? And this distance has to be 97.5. Yes? So you have a calculator. Put in. Do you ever know how to put in negative 142 plus 97.5? Or, how about not or? And plug in 53 minus 97.5. Plug them both in. Does that seem like a logical answer? No, it can't be over here. But if I'm just randomly thinking, well, oh yeah, 97.5 sounds good. Wait, put that out on the number line. That makes no sense whatsoever. Does everybody have a midpoint? Are we good? This group is good. You didn't ask me how to factor. Amazing. Make the assumption that everybody can factor. 19, you were good? Good. All right, we're done. Let's pass them in. And I'm going to come around and look at your postulates and theorems. Okay. Did you write theorems also? There are theorems in lesson 4? Theorem 1, 4-1, 4-2, those are important. You have your others also? I'm not taking a grade on them. What happens is there's your 8. Well, that's why I'm not assigned 8 more. And I just don't want you to forget them. Yes. So when they draw stuff, you can draw it. The one with the 2 planes, it's hard to draw sometimes. Alright, so today we're going to look at lesson 4. And we're simply going to talk through what these postulates and theorems mean. Oh, there we go. I know I had it up there. Lesson 4. Postulates and theorems about points, lines, and planes. On the side, I think it's page 21, maybe? Yes. Page 21. There's a little hint on the side. Everybody see that? We've talked about postulates. Does anybody remember what is a postulate? What does it mean? Okay, it's true. It's a statement that we accept as true. No proof needed. No proof needed for a postulate at all. Theorems are different. Okay? A theorem must be proved. So let's read that little hint. That's what we're going to read. Unlike postulates, theorems must be proved to be accepted as true. So theorems must be proved. To be accepted as true. So that it must be proved. Somewhere, every theorem we're going to talk about, every theorem that's in this book, is proven somewhere in this book as an example, or they're going to ask you to prove it. Okay? Theorems are great. We can't accept them as true, but if you can prove it, then it's true, right? Okay? So it's kind of like, well, what's the difference? Well, there's still a lot of difference. We could kind of argue about a theorem, but it will be eventually accepted as true.
All right, will somebody read postulate 5? Anybody want to?
All right, Jelena, go ahead.
Through any 2 points, there's exactly one.
Through any 2 points, there's exactly one line. You've heard that before, yes? 2 points make a line. Any 2 points, how many lines can I draw through 2 points? That postulate says there's only one. Okay? Theorem 4:1. Sadie, will you read it for me?
The 2 lines intersect and they intersect at exactly 1 point.
Okay. So close. Okay, I've got this little shape up here. Okay? Do you see that they all go through points A and B? Do we all agree with that? Okay? How many, so when I ask you, don't say anything out loud, how many lines go through AB? How many lines go through AB? Point A and point B. You have an answer. You have a thought in your head. All right, hold up a finger. 1, 2, 3, 4, 5. I love that there are different numbers being held up. What did we just read in postulate 5? And that we accept as truth.
Through any 2 points there exists exactly one line.
Okay. Even if I took off this last piece, theorem 4:1 says 2 lines can intersect only at 1 point. I just made 2 lines intersect at 2 points, right? Are they both lines? Are all 3 of these lines? What is the definition of a line? What are the first definitions we wrote down? Points, lines, and planes. Not meaning to be tricky, but geometry is a little tricky, right? You're changing your answer. Some of you, like, oh yeah, there has to be 3. Not telling on anybody. I've gotten the answer 4 today. Okay? It's okay. It happens. Okay? It tricks you, and I don't want to trick you. You have to know the definition a line is a straight path? How many lines go through AB? One. Okay? The curve is not a line. Not a line. This V is not a line. There's one line that goes through points A and B. Okay? So they try to do we'll look at example 1, where they have a line 1 and a line 2 and an AB. And they try to tell you that you can have two lines that intersect at two different points. Okay? Well, let's look at that one because I want to read it on page 21. At the bottom of page 21, example 1. Are you all with me? Does the diagram show two distinct lines through A and B? Points A and B. Use postulate 5 and 41 and 4-1 in your answer. Okay? So now I hope you're going to recognize immediately no. Okay? But no doesn't suffice as an answer. Okay? So let's read their explanation. I generally am not going to make you write this much, but more than 3 words is necessary. Okay? Postulate 5 says that there are any 2 points, there can only be one line. In the diagram, 2 lines pass through points A and B. However, the curve in the diagram is not straight and therefore is not an example of a line. Therefore, 1 provides further evidence that the curve is not a line, since we know that 2 lines must intersect at 1 point, whereas the line and the curve intersect at 2 points. Okay? That is their answer to a simple yes or no question. Okay? Not a simple yes or no question anymore. Okay? So, that almost exact picture comes up a couple times. I'm going to say it because you've written it, and it just reminds myself. Theorem 4.1. When we have to prove Theorem 4.1, you will not be able to use Theorem 4.1 in the proof of Theorem 4.1. Kind of makes sense. It's why when we are defining something, we can't use the word we're defining in the definition. Okay? We've talked about that a few times. I will say it again and again. We won't be able to do that. Sorry, transitions. I'm trying to not have off the board stuff, like just open a new one each class. I don't know why, how. Sometimes I will, sometimes I won't. Oh, well. All right, on page 22. Riley, will you read postulate 6 for me? Something you've heard before, yes? 3 non-collinear points. Make a plane. Unique. In the past, we've said unique plane. This says exactly one plane. All the same thing. Theorem 4.2. Abby, will you read Theorem 4.2?
There's a line and a point not on the line with exactly one plane contains.
Do what? So, from the first one, 3 non-collinear points. Make a plane. Make exactly one plane. Okay? So, what did they do from postulate 6 to Theorem 4-2? What did they do? Did they add a line? Or did they simply connect 2 points? They didn't change the number of points on the line, on the plane. They simply just connected 2 lines. They connected 2 points, I'm sorry. They connected 2 points to make a line. Could I have connected A and C? Or I could have connected C and B. Would we still have 3 non-collinear points? Yes, we would. Okay? Keep going. Theorem 4.3. Axel, will you read 4.3 for me?
If 2 lines intersect, then there exists exactly one plane that contains them.
Okay? Using still the same 3 non-collinear points. Going to Theorem 4.2. Can I keep going to Theorem 4.3? What can I do to this drawing to just make it exactly like there in 4-3? Do I need to add a dot? Okay, what does it say though? Two lines that intersect, right? Can I draw another line, B to C? Is that two lines that intersect? Can I still simply have three non-collinear points? Everybody still see the three non-collinear points? I haven't added any more points. Okay? Still making exactly one plane. Okay? You see, I mean that's. And then they go on to say, sometimes the little words right below or above sometimes are good hints at what's going on. Okay? You don't write them with them, but sometimes it's good to read them. Postulate 6, theorem 4-2, and theorem 4-3 give conditions for determining exactly one plane. Any of the following are sufficient. 3 non-collinear points, a line and a point, and a point not a line, and 2 intersecting lines. So how can we say, go make exactly one plane? You can put 3 non-collinear points. You can make a line and a point. Or you can have 2 intersecting lines. Any of those 3 will determine exactly one plane. Is one better than the other? No. They're all equal. Alright. Do we need to look at, let's look at this one anyway. I love that they want me to draw one somewhere, but I'm not going to. Example 2, identify points and lines in planes. Can you name 4 points? Does everybody see 4 points on those 2 planes? And example 2. They're not very unique either. A, B, C, and D, right? What about 2 lines? 2 planes. I'm going to ask, can you name, I'm not going to ask right there. Time to ask that question. We're going to move on to postulate 7. John, will you read postulate 7?
The 2 planes intersect near the intersection is a line. Planes in the plane intersect at AB.
Have you heard that before? Yes. Everything we talked about in lesson 1 that we wrote definitions and the intersections of all those things, they're coming out now as postulates or theorems. They're amazing. We're very thankful for them. Okay? But now they're giving us something to use. Postulate 7 is amazing. Alright. They do more. Can you identify the section, all points? Can you look at that? Example 3. Can you name 4 points? You probably can name a lot more than 4 points. Can you name 2 coplanar lines? I'm asking different questions than they are. Somebody give me 2 non-coplanar lines. Should I ask for 2 coplanar lines? I'm going to ask for both. In example 3, name 2 coplanar lines. Why am I writing into that? And name 2 non-coplanar. In example 3. Do you have one or the other? Give me one or the other for right now. Paxton.
Line G, H, and C, D.
G, H, and C, D. Which one are they? Coplanar or not coplanar?
Coplanar.
G, H, and C, D. I agree. Are there others that are coplanar? Sadie.
G, H, and F, E.
G, H, and F, E. Any others? I don't see any more hands. What's going on? Are there any? Yes, Paxton.
Non-coplanar would be CD and FE.
CD. Everybody say CD and FE. Does everybody agree with CD and FE? Can I ask you a question about CD and FE? Do they intersect at point S? Have you written anything in your notes or a postulate or a theorem that says any two lines that intersect will be what? They must be coplanar. They intersect. They must be coplanar.
So there's no.
Oh, thank you so much for saying that, because you were going to sit there and wonder and wonder and wonder and wonder and question and question and question. Are there any lines that are non-coplanar?
No.
There are none. So that's what you're going to write. None. There aren't any. Okay? If they intersect, they are coplanar. Okay? If they're on the same plane when they go through it, GH is on both planes because it's where the planes intersect. Okay? See, I like that diagram much better than example 2. It's got a lot more stuff. It's a lot more confusing. Alright, we're going to go ahead and read the next 2 postulates. Lucas, will you read postulate 8?
If 2 points lie on a line, then the line containing the points lies in the plane.
Okay, let's read that again.
If 2 points lie on a plane, then the line containing the points lies in the plane.
Yes, we talked about this when it was intersections. When we had this. If the line lies in the plane, then their intersection is the line itself. Okay, we've written that down. Everything that we're doing, we've written down before. That's amazing. Makes me so happy. All right, postulate 9. Go ahead, Jackson.
A line contains at least 2 points. A plane contains at least 3 non-coplanar points. Space contains at least 4 non-coplanar points.
Okay. It gives the minimal number. So how many points does it make? Do you have to make space? 4 non-coplanar points. How many points do you have to make a plane? 3 what?
Non-coplanar.
Non-collinear. They can't be on the same line. Right? And then to make a line, 2. 2 points make a line. 3 non-collinear make a plane. 4 non-coplanar make space. It's in postulate 9. Alright, now my favorite example of the whole book. Example 6. Okay, Joanna, will you read the beginning of example 6?
Example 6.
I'm sorry, 4.
Okay,
What?
yeah.
I wrote 6. I don't know, I'm excited. I'm getting ahead of myself. Woo. There's not an example 6 here.
Okay, I was so confused. I was like, you're looking at the wrong paper.
Sorry.
Often small tables have only 3 legs. They have the advantage of not tipping if placed on an uneven surface. Use postulates given in this lesson to describe why this is true and why a 3-legged table will wobble less than a 4-legged table.
Okay, usually at this point I have a chair. I gave 2 of my wobbliest chairs away. I was so kind. So in your chair, can you wobble back and forth? This one does a little. It does a little. There's 4 points on the end of this chair, yes? Does everybody say 4 points? You sit it down, and it wobbles. Why? Why in the world when they say a three-legged table would wobble less? Why, when you go take pictures, professional pictures, what do they set the camera up on? A tripod. How many legs does it have? Three. No matter how up and down and off they are, 3 legs, 3 points will always make a plane. What happens if I have a 4th point that's not on the same plane? It creates a wobbly chair. It's space. We're not happy all of a sudden because we're wobbling. And one that really wobbles. Okay? That's what happens. These 4 points are not all on the same plane. They're not all level. So they're not on the same plane. But if you just have 3, no matter how up and down they are, how rocky your surface is, I think about the people that survey, right? They're surveying in the woods and on the sides of roads, and they're having to let out one of their legs of their tripod. Okay? But wherever they have it, it's going to be sturdy because those 3 points will make that solid plane, even if it's going down on the side of a hill or something. Okay? Kind of makes sense. What postulate is that?
Postulate, last one, 9.
I'm going to say probably not.
Postulate 6.
Maybe postulate 6? You think postulate 6? Because there's your solution, you read it to get the answer, it shouldn't be the answer. It's definitely not postulate 7. Yeah, any 3 non-collinear points makes the point. That should be your postulate 7. You may go when I got homework tonight. You go and have a great afternoon. What was postulate 6? Yeah, no.
Oh, I thought you said it was 7.
And
No, it's
if you
not.
look at if you look, okay, go back to page 22 or 23. What I was trying to say, it's not.
Got it. Yeah, I finished mine. No.
Yay! Oh, put out the chairs. Not Camden, you're Gary, your little brother's Camden. Sorry. Oh, sorry.
He's fine.
So sorry. I'm sorry, Margaret Ann, it's all okay. Sorry.